Hello, my name is John Lacey. I'm the director of the Global Mining Law Center here at the James E. Rogers College of Law. And what we want to talk about today is in connection with our mining law in space. Obviously the concept of the global mining law has just taken we've taken a leap going on to the extraterrestrial application of law. And I have as my guest today Dr. Spencer Titley, who's an emeritus professor of geology here at the university. And I've called him the first lunar prospector. I don't know if you agree with that terminology, Spence, but I think that
Well, there were not many people interested in
there's
prospecting.
there's not many people that can challenge you
It's a small field.
on that. This interview, in some respects, is an extension of an interview that we did back in 1964, and this was an article that was written for the Arizona Wildcat on my interview of Dr. Titley. For this, you had a contract with NASA to do geologic mapping of the moon, didn't you?
We had that. We worked through the U.S. Geological Survey branch of astrogeology at Flagstaff. Gene Shoemaker came down to the department in about 1962 seeking contact with people who would be interested and who he could support in the strange thing known as mapping of the moon. So we said, sure, why not? And we got started there. We put USGS geologists through our academic program, and we opened it up to other planetologists, and we started in 1962.
And the facilities that were used here was what?
On campus, we simply used what we had in terms of mapping of stereoscopes and this sort of thing. And we were aided by acquisition of data from the Pierce McMath solar telescope on Kitt Peak, which we used quite widely in terms of looking at the moon.
Now, as I recall, we had the lunar image was projected on the plane table there.
That's right. The solar telescope is not of much use to people interested in the sun at night. So, and the people that would work at night are not terribly interested in the sun. So the planetologists and the people interested in the moon could use the solar McMath telescope for imaging, particularly of the moon, and that's what we did. We projected an image of the moon onto a flat surface, and from this we magnified it, and we get all sorts of detail that we couldn't get from photographs. So,
as part of that process that we talked about, that there's the moon moves a bit.
yes.
And you want to talk a little bit about how that impacts your ability to do the mapping?
The moon, I'm not sure the total figure, but it librates. It rotates very slightly to some 4 or 5 degrees, as I've been told, and that allows you to take 2 pictures at extremes of this libration and look at it in 3 dimension with a stereoscope. The moon does move, but we see light and dark spots on the moons through a 28-day cycle, and we see a morning sun and an evening sun, and the line between them of darkness and light is called the terminator. And what we would do with the telescope would be to pick the terminator that is closest to the area in which we were interested and work along the terminator, which would limit us to 3 or 4 days in the first lunar period and 3 or 4 days in the second. So we'd have somewhere between 6 and 8 days when the terminator was at the right place to enhance the topography. So we used the telescope, and we used what were a very high quality set of photographs, the rectified lunar atlas put out by Gerard Kuiper and his folks at the Lunar Lab at the University of Chicago. So good telescopic photographs from a variety of telescopes around the country, and the use of the telescope were our two means of acquiring data and putting stuff down on the map.
The geologic ages, and I took this information from what you told me about 55 years ago. The most recent craters being the
Copernican,
yeah,
and Procularum, and then the Imbrian.
and now we've talked about this mares of possible volcanic origin. Is the moon like the same dynamic as the Earth, where we have certain tectonic plates moving around?
Well, no, the whole view of the evolution of the moon has changed in recent years. I haven't kept up with it too much, but the way of thinking now is that an impact on a primitive Earth, maybe about 3.8 billion or 4 billion years ago, carved a big chunk of the Earth out and it became the moon, which underwent its own sequence of melting and stabilizing its figure. And again, this is stuff that I really have not touched into, but we see on the moon big areas, flat areas that are dark, and hatch up areas that are bright or dark, and that period, and what we do is separate the various kinds of surface features, topography that we have, together with the brightness of the rocks and the position of the rocks, to come up with a sequence of things that might have happened on the moon. And from this we have defined the Copernican, for example, as the bright rayed craters, the ones that we see when the moon is full. Mm-hmm. The Procularum are the very dark areas, the mares, or the oceans as they were called, are possible volcanic origin. We believe we did believe, I don't believe there's much change in this based upon more recent research on the moon, that they are from magmas that flowed perhaps during an early stage of melting of the moon. And then they were impacted, or actually they formed in what we believe may have been large impact basins on the moon. The mare filled the basins, and then we have events that took place that cut across the mare rock. In other words, we see big flat areas with craters on top of them, which gives us a sequence of cratering which has taken place since the mare formed, which are a product of melting, we believe. But in terms of volcanic stuff, as we see on the moon, as we see on Earth, we searched long and hard for it. It was a challenge to a group of some 10 of us that were involved in the mapping at Flagstaff to decide whether or not the craters we saw were volcanic origin or of impact origin. I believe the consensus now from what we've seen is that probably 90 plus, 95 plus, 98 plus probably are of impact origin, with a small amount being possibly of volcanic origin. So we're looking at,
if you have a volcanic origin, how would that have come about?
we're not sure. That's one of the problems of how we do it, because that involves internal heat, and we don't quite know what the internal heat on the moon is, so that it's hard to say whether or not we went largely on the form of the crater, the freshness of the rim, the size of the crater, and from this we'd put down volcanic query. It wasn't a very popular interpretation among many of us, and I would be surprised if there isn't a crater of some sort that formed back during the time scan that we're looking at that may have been of volcanic origin, but what we see now are dominated almost overwhelmingly by the effects of impact.
So I take it from that, if you really don't have a volcanic origin, the likelihood of similar types of mineralizations that are related to volcanism on the Earth would not exist on the moon?
Well, I haven't been there. It's not likely. We can't deny it. When we look at the large dark areas of what we call mare, we believe these are ultra basic flows. They must have had a source somewhere within the moon that came out and flowed into basin where the level was reached, where they saturated or became hydrostatically equilibrated with each other, because they look like they're all of the same age, the big Mare, and they, I suppose you could say they were of volcanic origin, but they appear to be melted rock, and the Earth may have had a similar history, and the melted rock maybe just flowed into these basins without a volcanic superstructure. When I think of volcanic phenomena, I think of craters and mountains that form originally over the top of a heated body of rock, and through which we have ejection of deep hot magma as rocks out of the top of the mountains, which makes so we have a combination of both the landform and the rock type and the temperatures that drive the systems. And we simply don't see a collection of those things in the proper order, or at least I have not recognized it, nor have I heard it recognized, that we have definite volcanic features that we can point to and say, oh, that's a volcano. Mm-hmm. We can't say that the Mare did not originate by melting of very primitive material and become magma, in the sense that we see magma fields in, for example, in the northwestern U.S., of simply rocks that came out and flowed over the surface rather than evolving from a constructed feature of explosion that made a mountain peak and a crater on its top.
These geologic ages that we have listed here, is there any equivalent on Earth?
Well, we have. There's a period of time that goes back well into the Precambrian on Earth, in which we see a great number of remnants of impact that made craters on Earth, the same thing that we believe may have happened on the Moon. And so we have in this crater period, which would see, I don't know, 2+ billion years back to 3+ billion years ago, maybe even further, there was a time, and we see remnants on Earth in a number of places. In this point, we're increasingly recognized phenomena that may have that may have originated by impact. But this was a time of impact things on Earth, and we've been able to date them. I think the date of 3.8 marks a boundary between the development of a high volume or a high number of impacts on Earth, which swept up the material in our orbit, and we finally cleaned that out. But we still see impacts on Earth today, and we're simply cleaning up the orbits.
So really, these geologic ages would probably be equivalent of some of the very oldest geologic ages on Earth.
That's right. Except for some impacts, the Moon is a very old feature, and some 90% of it is old. And by old, let's say it's 3 billion years or more. I'm not sure what dates have been developed, but I think there are some in the range of 3 to 3.5 billion years for some of the rocks returned from manned flight.
Yeah. So in other words, too, is that the probability of mineralization on the Moon would be the same thing as associated with the extreme oldest geologic epochs on Earth.
We are dealing with old rocks on the Moon, and we are dealing also with young impacts, and we don't know what goes on with some of these things. The bright rayed craters of Copernican age, these are the most recent ones, and when we see the full moon, we see these bright spots splashed all over the moon, and these are bright ray and the bright ray material, which is crushed rock, we believe, that has been thrown out all over the moon. Tycho, and Copernicus are the two most dominant ones of these that on the western side of the moon as we view it, and the older ones that we see remnants of very old impact on the moon that in which there are remnants of craters that could constitute the jagged highlands of the central part of the moon as we see it. So we don't, the probability, I would have to say, based on what I know and what I understand we know, of seeing a style of mineralization related to a volcanic origin as we understand them on Earth is very, very remote based upon what we now know about the moon.
Okay. Well, let's take a look at a couple of your images that came out of your study. This is the Mare, was it Humorum region? Is that
Mare Humorum region, yes.
And what are we looking at here?
The center part of that is a Mare surface, a flat surface. It's dark. When we see the full moon, these are the dark patches that we see scattered across its face. This Mare is in, if we look at the moon and look at north and south as we view it on Earth, this is in the southwest quadrant of the moon. You can see it. It's a round, very distinctive black spot in the southwest corner of the moon. And it has a Mare surface on it, and you can see that it is rimmed by highlands, broken up rocks. And you can see a number of places where craters cross the rim of the basin, particularly there at the top. And it cuts the rim of the Mare Humorum basin. It's therefore younger, and we would say that this is post-Imbrian or post-Mare, and it could be either of Eratosthenian, which is one range of ages, or Copernican. If it had bright rays in it, we would call it of Copernican or of the youngest age, but it's a crater that we had assigned to the Eratosthenian, which is named after the crater Eratosthenes. And these are sometimes Mare florid maidens. You can see at the bottom of that map some craters also that are near the rim of the Mare Humorum that have a flat black top on them. So there's Mare material, apparently rocks that flowed, or they came from magmas that flowed, we think, and formed after the Mare Humorum filled itself. There are two craters down there at the bottom. You can see their bright edges, and you can see the rim of them, and they have flat floors that are dark. So we assign to them a Mare age after the Mares that we see spread across other parts of the moon.
Okay.
In the very middle of that, I point out there's a very bright spot in the middle. That's a very, very young crater. And how young, I don't know, but that would be Copernican. And those are the bright rays, that's a tiny crater. It has bright rays around it, okay. And that's the very youngest one.
Now we have part of your mission here was to identify Apollo landing sites.
Yes.
And we have a couple images here of those Apollo landing sites. What does this image show?
It shows a whole bunch of craters. This is at a completely different scale than the previous one. It's located on the northeast side of it. And you can see as you get down and get more and more resolution, you can see that the floor is pretty well dimpled from the effects of the impact in creating both crater rim material and crater floor material. You can see there on the fold and in the top middle part of it, a bright crater with bright walls in it. That's the younger one. And the Apollo landing sites, of course, were designated, as far as I know, as far as I've been informed about it, were placed in places where we could see a critical juxtaposition of different kinds of features and different ages of rocks, and would be relatively safe in terms of landing and have a high probability of stabilization when they did land, such as you can see in the southeast corner of this map, smooth area. We're in the an area where we designated one landing site. I'm not sure if Apollo flew there or not.
Okay, let's take a look at this next image, Spence. This shows some of the landing sites, and the scale of this is what?
1 to 100,000 at the scale in which it was mapped and produced. And the distance across the crater at the top is probably around a mile, more or less. You give it in the section of a landing site. We did one thing that we do on Earth, and that is when we map a mountain range, we go into the creeks that drain a mountain range and sample the creeks to find out what kind of rocks were got from the top. So that if we can pick an area that's low, that is draining, as it were, or in which talus or rock balls come, we can get by sampling a few rocks, we can get some idea of what lies above us. And that's pretty much one of the things that dictated where we might find a variety of rocks surrounded by elevated regions that would give us, in a few rocks, a lot of information.
Okay, and so the idea was that to put the landing sites where you can get the most information
Safely.
safely.
Yeah.
Right? Obviously, you don't want to land on the edge of a crater.
No.
Okay, so basically the little ticks that we see along the boundaries of that grid would be, approximately a mile.
Yep. And you can see the circles in there that are sometimes landing sites, but they're the depressed areas. And who knows what they were. I'm not sure they ever got into a depressed area.
Mm-hmm. In terms of the resources of the moon, my question initially was, what information did the Apollo geologists bring back? And so essentially we've only had one geologist that's actually
right.
been on the moon.
Yeah,
That
Jack
was
Schmidt.
Harrison Jack Schmidt.
Yep.
He was on one of the Apollo missions.
He was on the last one.
And do you know what he was particularly interested in?
I heard him give a talk. We haven't talked. We talked early on in the program, and we had a lot of communication when before the scientist astronaut program was even developed. And but I'm not sure what his mission parameters were. I wish I knew, but I've seen him a couple times since he's been back, but I've never had a chance to talk to him.
In the mineral values that or potential mineral values on the moon, a lot has been written about helium-3, and you want to talk a little bit about what helium-3 would be all about?
You're going to be in better shape than I am on that.
Okay.
I'm sorry.
Well, I think that certainly one of the things that we've talked about, or that they've talked about in the presence of helium-3, is that it occurs in the regolith. In other words, the top part of the moon's surface.
The soils, as it were.
How deep would those lunar soils be?
I can't give you a good answer on that. I'm thinking on the order of tens of meters.
Right.
This is a very, very old surface. This is where it's not cratered, and where we have, let's say, either mare or upland. We're looking at the possibility of, in the mare, of a few to tens of meters, I'm guessing. In the uplands, if it's here's the thing, when you form a crater, you create a lot of unstable rocks in the rim. The rocks are uplifted and they form sharp rims and this sort of thing. And every time you get another impact, what happens is the ground will shake a little bit, and what happens is the minerals shake down. And a portion of that is going to be the fine grain material formed during the impact, plus the coarse grain. So I would expect, if you drilled a hole, you would probably find a conglomeration of broken rocks together with very fine grain material, and that this might constitute a typical lunar soil, which might be on the order of tens of meters of thickness.
Do you know if any drilling took place on any of the Apollo missions?
I believe they had core samplers. I believe they did bring back samples of soil that were present, but I'm not sure what the results of any of those studies were.
Do you know what depth they went to?
No, I have no idea.
But it would have been probably fairly superficial, wouldn't it?
Yes, yeah. I don't think you have enough length of drills to worry about getting all that stuff. I just don't know what they got.
And helium-3, the processing of that, as I understand it, would require about 150 million tons of helium, or of dirt, if you will, would have to be processed to wind up with 1 ton of helium-3. So from your understanding, that would take an enormous amount of the lunar surface in order to recover that small amount of material.
That's true. I'm basically an economic geologist, and I work in mines and what is possible and what isn't possible, and so that's been my principal field. So that when I look at these things, and helium-3, the one thing that occurs to me is you must really want to want this. You must really want to watch this stuff terribly badly. You want it.
In order to spend the money that's required
to spend the money
process it.
to get up there to process it. And maybe we're looking at stuff that's decades down the line. I have no idea, but from my standpoint and the work we've done with other stuff through the national academies, this would be an expenditure of money that would be far above and that of even the flight itself. To get down there, first of all, as I understand it, the concentration of helium-3 is in the materials that are away from the sun. They're down or in the colder spots, I guess, which would be at the bottom of the moon, which would be dark, or dark in places, long shadows. And you have to establish some sort of energy system up there to start mining the soils and moving it around. So you have to fly this stuff into your machinery or whatever it's going to be that you're going to process the soils by. And I just see at this point in time, based upon our mineral values now, our expectations, and what we know about these things, an extraordinarily expensive process to get into these things. Now, I don't know about what other nations are doing with this. I understand there are other people that are interested, other folks on the planet that are interested in the helium-3. I don't know what they're doing, but they must have a lot of money to do it.
So it's going to take both a lot of money and an enormously large area to look at.
It's a large area to look at, and there, conceivably, we could find this at the bottom. Any one of these areas, actually, that are flat appearing, may have some small craters on it, but this would be an area where you'd look at the soil. But to me, it looks like a very expensive proposition and something that you really want to get at. I don't know what else is up there, and I haven't seen a good mineralogical analysis of lunar rocks. I'm sure some exist in the literature, but I haven't run them down. And if I had a better idea of what the minerals were like, why, it'd be fun. I did some work with a graduate student, and I believe it was in the Lunar Lab, Planetary Sciences, some years ago, which I thought was very interesting. The kind of rocks that we see in the Mare are very dark rocks, and these are ordinarily rich in titanium on Earth, if they're the same thing. At least that's an important accessory element in some of the minerals of these very dark rocks. And his thesis dealt with the processing of rutile, or titanium dioxide, to get the oxygen out of it. And I thought this was a very clever way to get at it. It would be, if there is rutile in part of these dark rocks, this would be a source of oxygen tied to titanium and perhaps available. But I have no idea where that thesis went, or whether anybody's even considered that, or whether it's even a valid suggestion.
So with the possibility of having oxygen there, that would lead into the possibility of making water out of it.
That's right.
As a source of water.
Yep.
Yeah.
Yep. There are all sorts of interesting things. If we could just get oxygen in there to do these things, then we could do it. Who knows? I'd have to leave it to the people who've studied the minerals of these rocks that are down in Houston. A former graduate student of mine, John Anthony's Bob Lawn, was curator of that bunch of rocks from the moon at Houston. I don't know, I haven't seen Bob in some years, but he sits on top of them.
Yeah.
But we need good mineralogical analyses to know what we're dealing with.
Okay, and this really brings us to the issue of what sort of laws might be applicable for lunar mining, and it seems obvious that there's going to have to be an international sharing of information.
And money.
And money drives it all. And that question is whether or not this is going to be done financed internationally, or whether or not there's enough private money to get into it. But certainly the idea of certainly having qualified developers in the system, and whether or not that's done by consortiums of private entities or consortiums of government. Certainly we've looked at concepts of private claims for exploration initially, and then selecting prospective areas for ultimate development, and to release those lands not selected. Of course, we've talked about how if you're looking at things like helium-3, that the control of the regolith of the moon soil needs to be very large, and considering the amount of material, you're looking at creating processing plants at the site because of weight factors on a return to Earth, and certainly separate heat sources. And obviously, if we're looking at very cold areas of the moon, the production of energy and heat is going to be a critical concern.
Well, the whole question of energy in these systems has been a matter of discussion and all sorts of meetings, this sort of thing. I have some reports here from various committees I've been with at National Academy looking at the heat problem for both the space flight. There's a dichotomy of sources here within the range of Mars. The sun and the solar energy is available to do a lot of things at Mars, but beyond Mars, the effect of sunlight is very minimum. And what you have to do is go to radioactive sources, and the one that has been used most commonly in these distant flights is plutonium-238. Plutonium-238 was produced and it was stopped being produced when we stopped making stuff for bombs, which was about 1980. And the long distance flights have used Stirling engines with the helium, plutonium-238 as the driving source in it. And that's about 600 degrees, and 600 degrees centigrade would be required. So over a period of 10 years, they were hopeful to be able to create a few kilograms of this stuff by restarting some of our systems here in this country. The Soviets are reported to have had quite a bit of helium-3, and the available helium of plutonium-238 plutonium-238. About half of our, as I understand, about half of our available plutonium-238 is defense-related, and the other half has been science-related. And we were running out of it very quickly here some years ago, but I believe they've restarted some of the processes necessary to get to, I believe it's neptunium, one of them that decays and becomes plutonium-238, which is an alpha emitter. It's simply alpha particles, very, very high temperatures, so that if you're going to look at something to separate helium from the fines, you're going to have a temperature source which is in the range of the plutonium-238 to get to the 600 degrees centigrade required to release the helium.
Yeah, good.
But
good.
Lots of money. These are interesting things, and
and money's going to drive it all.
Sure. We talk about international cooperation. I keep thinking about the Soviet Space Lab that's up there, that we've had a whole bunch of folks of different nationalities and political sources become partners in that. And so there's been a good partnership in that as far as I understand it. I don't know if you read, this is another aspect of this. I've read the short story by Kelly, who spent a year in space, and in a sense this is scary because it's a complete detailing of all that he went through and what he felt and this sort of thing. And he felt, one of the things he felt so strongly when he got back on Earth is how heavy everything was. And this is just a year of flight, and if we're looking at some of these things that have a longer time on the moon, which has a lowered gravity, there's a component of humanity and of our physical capacity to work in these environments and come back. I believe Kelly had to spend some time in the hospital. His recovery from this is really a tale of really stress. He felt fine in the capsule, but when he got back to Earth, it was hell.
Yeah.
I don't know if you've read that, but it's an interesting account of.
Well, I think there's all sorts of separate things to consider.
Well, yeah, this is one, and then one is the human factor in this. So maybe we'll be working with robots by then. Who knows?
Could be. Well, Spence, thank you very much for going through this with me. I know that when I read some of those initial articles that we were doing back in the early 1960s, you said you were too old to participate as an astronaut, and
I was 1 month too old.
1 month too old.
Yeah.
Well, that's,
But Jack Schmidt and I worked together up at Flagstaff during the summers, so.
yeah. Well, you got to participate in the program very nicely.
Well, yeah.
Well, thank you much for
My
doing
pleasure.
this today.
My pleasure.